Hello everyone, my name is Ali Turani and I'm going to present you the late-breaking results on visual S-graphs for robust semantic scene understanding and hierarchical representation. Vision sensors are able to supply rich visual information and enabling the extraction of semantic information, which are high-level information acquired from the environment through processing visual data. Accordingly, fiducial markers are the tools that can aid VSLAM systems in detecting semantic entities while reconstructing a map due to their unique identifiers and can provide valuable pose information. Although there are some marker-based VSLAM frameworks out there, such as UcoSLAM and TagSLAM, they purely create geometric map representations. So, the main motivation for the current work is to implement a marker-based optimizable VSLAM that creates accurate maps from the environment through adding new semantic and geometric constraints for such accuracy enhancement. The framework also augments hierarchical representations to the reconstructed map using semantic entities. Here you can see the pipeline of the proposed method and its constituent components. The framework is built upon VSLAM and benefits from a multi-thread architecture for processing data. The generated situational graph of the proposed approach is depicted here. You can see that it incorporates semantic constraints including walls, doorways, corridors, and rooms. The pre-existing geometric constraints have been complemented with semantic constraints acquired with data of fiducial markers. As for semantic entities, markers are crucial reference points in the framework, enabling the system to interpret and contextualize semantic data. Walls are the plane-shaped entities on which markers and their surrounding visual features are located. The equation of a wall in 3D is obtained from the pose of the markers attached to it. Corridors are comprised from two parallel walls, which are labeled with ARG markers, and their center points will be added to the map. Likewise, rooms contain four walls with two pairs of perpendicular labeled walls, constraints over the walls forming them. Finally, doorways are the next semantic entities in which the pose information of ARG markers placed on them are employed for mapping. Additionally, introducing a new generation of markers that are imperceptible to humans but visible to robots under certain lighting conditions with a specific camera setup, along with validating their applicability in robotics, is another contribution of this work. The detection of such markers involves leveraging particular optical components and computer vision methodologies introduced in a previous work done by the authors. For evaluating the performance of the proposed method, labeled as visual S-graphs, in real-world conditions, a 3D LiDAR sensor and an Intel RealSense depth camera were mounted on two-legged robots. The robots collected data provided by sensors while traversing various indoor environments with different configurations. Each wall and door of the environment were labeled with printed ARG markers, and the unique identifiers of the markers were stored in a database to fit the method. You can see the characteristics of the collected indoors dataset here. Accordingly, various experiments have been done on the proposed approach, UcoSLAM as a marker-based VSLAM, Semantic UcoSLAM, and VSLAM as the baseline. Also, due to less noisy outputs of LiDAR sensors compared to vision-based sensors, S-Graph Plus as a LiDAR-based framework has been used to produce ground truth data. Regarding the evaluation results presented in this table, we can see that visual S-graphs outperform its baseline counterpart and other frameworks across various scenarios. This enhancement can be attributed to the ability of visual S-graphs to introduce new constraints to the map through the association of semantic entities. We can also see the qualitative results and absolute trajectory errors of the proposed approach with respect to translation in meters on some dataset instances. It should be noted that some of the markers employed on door frames was imperceptible, and given that the sole distinction between such markers and ordinary ones lies in the detection step, the resulting semantic map remained unaltered. In conclusion, this work introduced a VSLAM framework that effectively harnesses the outputs provided by RGBD cameras to achieve highly accurate map reconstructions, along with generating optimizable multi-layered situational graphs with semantic entities.